Hello everybody, welcome back to 1D kinematics. This is the video where we go over the practice problems, and I have 3 of them here, which are all relatively easy, but they all have one difficult part to them, I believe. Now we're starting off. The first one, actually, if you look at our rating scale to the right, this is our rating scale, so each extra star indicates a level of difficulty for that particular part of the problem. So I accidentally crafted it so that way the first part has 3 stars, but we are going to go along with that. So let's get that first problem out of the way first. If you want, you could skip through that and then go back to it at the end of the video, but I personally really enjoy doing it in this order. I think it's better. I will link a PDF to this in the description down below, or you could take a screenshot. I don't think anybody's going to want to take a screenshot, or you could just write this out down on a paper and go along with it as I go. So let's get going. For this first question, we have a ball that is dropped from a height of 4 meters from the surface of the earth starting at rest. So let's start a box of what we know. So we know that delta x equals 4 meters. Since we are dropping this, let's say if it's off of a hill, let's say there's a little guy dropping it. So this height is 4 meters. And then since it is at the surface of the earth, we know A is equal to G, which is the gravitational field strength, which we are given is equal to 9.81 meters per second squared. So then we also are given that the ball is dropped starting at rest. So that means that the initial velocity, VI, is equal to 0 meters per second. So that gives us enough information to do our first problem. The first question, how long does it take for the ball to reach the ground? This is just an equation. So we have delta x equals VIT plus 1/2 AT squared. We are looking for t. We have delta x is 4 meters. We have VI is 0 meters per second times t, which crosses out since 0 times anything is 0, plus 1/2 times 9.81 times t squared. So we have 9.81/2 times t squared equals 4 meters. So when we divide both sides by 9.81/2, we get 8. I forgot to write meters per second squared here. We get 8 meters divided by 9.81 meters per second squared equals t squared. Take the square root of both sides, and we get t equals radical 8/9.81 times seconds, since that is our units. So I actually do not have a calculator on me, so I'm going to grab one real quick. I'm just going to grab my phone, but I don't know how I didn't think of grabbing a calculator before I started this. So I will plug this all into my calculator now. Let's go. Radical. So for our time, we get t equals 0.903 seconds, about. It goes on for a while because it's an irrational number, but we do not care about that. We only care up to 3 decimal places. That is part A done. B. So in this part, we are looking for VF. So we have the equation VF squared equals VI squared plus 2AD. Now, in this equation, we have everything we need, where D is delta X. So we could just take the square root before we even do anything, and we get VF equals the square root of VI squared, which is 0 meters per second squared, plus 2 times G, which is 9.81 meters per second squared, times delta X, which is 4 meters. Sorry, that is getting in the way a little bit there. So we get VF equals radical 2 times 9.81 meters per second squared times 4 meters. And then let me plug this into our calculator. We get VF equals 8.859 meters per second. Now this problem is very difficult, and I'm not even gonna try to solve it, or I'm not even gonna plug everything into the calculator until after it is completed. So I'm going to take this work, move that up here, get that out of the way for now. I left a little bit of over there, but that doesn't matter, it's fine. All right, so this question is a very difficult one. Now, assuming the collision with the ground launches the ball back up 2 meters in the air, and the time of collision with the ground is 0.5 seconds, what is the average acceleration of the ball during its collision? So, we know from the previous problem that the velocity of the ball as it hits the ground is 8.859 meters per second squared. So, once it bounces off the ground, it returns to a height of returns to a height of 2 meters. And the time it takes is 0.5 seconds. Actually, wait, that doesn't matter for this part of the problem. We can move this over here. So delta X equals 2 meters, and then we have VF equals 0, since it launches up to a height of 2 meters and then stops and then falls back down. So it goes up and then it goes down, and then at the height of 2 meters, the velocity is 0. So we know also G equals 9.81 meters per second squared. Now, our initial velocity is what we are looking for in this problem. So for this question, we can once again use the formula VF squared equals VI squared plus 2A, or in this case G, times delta X. So VF equals 0 meters per second squared. VI equals, oh, also, forgot to mention this. Wait, VI equals question mark meters squared. So just VI squared. So we are looking at this direction as the negative direction and as this direction as the positive direction. So anything going up has a negative velocity, anything going down has a positive velocity. And then since gravity is going down, that would mean that gravity is positive. So we have plus 2 times G, and then multiplied by delta x, which is 2 meters. And then this is 9.81. So we have, then we subtract VI, and then we get VI squared equals, these are in opposite directions, so it's 2G, 2 times 9.81 times, this would be negative VI, and then since the displacement is upwards, that means that it is negative, so that means that this would be negative 2 meters. So we would have negative 4 meters times 9.81 meters per second squared. And you would take the square root, and that is equal to, forgot about one small thing. I'll just get rid of this. So then we have to get rid of the negative. So we have to multiply both sides by -1. So then we get VI squared equals 2 times 9.81 times -2 meters times -1. So the -1 and the -2 cancel, and that just becomes 4 times 9.81 meters per second squared, and then this is meters. Then you take the square root, since that is equal to VI squared, and you get the answer for the initial velocity to be 6.264 meters per second. But we are looking for the average acceleration, which we have to use a different equation for this part, which we use the equation A average equals delta V over delta T. So we are given delta T is 0.5 seconds, since that is how long it takes for the ball to collide with the ground. So we know, and then our delta V is 8.85 minus negative, here, I'll clear some of this stuff out of the way. Do this in a different area. A equals delta V over delta T, which is equal to, so we are redefining this as positive, this is negative, since this is a new part of the problem. So our velocity over here becomes negative. So we have 8.859 meters per second. I don't know why that's a squared up there. Minus, and then negative 6.264 meters per second, all divided by 0.5 seconds. So we have A average equals 8.859 meters per second plus, since minus times negative equals plus, plus 6.264 meters per second, all divided by 0.5 seconds. So we have our final answer. I'm plugging it in right now. 8.859 plus so we have our average acceleration is equal to, also the magnitude is equal to 30.246 meters per second squared. That is our final answer for the super difficult question. That is the most difficult question of today. Do you like all of that work? Yeah, that is a whole lot of work. It only gets easier from here, though. So, question 2. A ball is thrown down at an initial velocity of 4 meters per second, so VI equals 4 meters per second. And it takes 2 seconds to hit the ground, T equals 2 seconds. This is also assumed to be on the surface of Earth. If a problem doesn't tell you it's not on the surface of Earth, you assume it's on the surface of Earth. That's true for all of AP Physics. So you have G equals 9.81 meters per second squared. So the first question, what is the height above the ground initially? So in this case, delta x equals h, and we're looking for h. So we could use the formula h equals VIT plus 1/2 AT squared. And then we have h equals VIT is 4 meters per second times 2 seconds plus 9.81 meters per second squared over 2 times 2 seconds squared. So we get h equals 4 times 2, 8 meters, since seconds and seconds cancel, plus 9.81 divided by 2 times 2, so the 2's cancel, and then, times 4, this is times 2 squared, so it's just 9.81 meters per second squared times, divided by 2, times 4 seconds squared. So the seconds squared and the meters per second, and the seconds and the 1 over second squared cancel out. And then we are left with h equals 8 plus 2 times 9.81 meters per second squared, which gives us the answer of h equals 27.62 meters. So for part A, we have the answer of h equals 27.62 meters. Now let's move on to part B. Oh, that's not what I meant to do. Alright, I quit. Can't move that. If I need to, I'll erase some. I'll just start by erasing a little bit now. Let's see. So for part 2, we have what is the final velocity of the ball. So now we are doing the same thing. We are just looking for VF. VF equals a question mark. Now for this problem, we will be using the formula A equals VF minus VI over T delta T, where we don't need a delta, but I'll put it, which is equal to G, since A equals G in this case. So we have 9.81 meters per second squared equals VI, or VF, which is, VF, which is VF minus 4 meters per second, all divided by the change in time, which is 2 seconds. So rewriting this, we get 2 times 9.81 meters per second squared, 2 seconds, so this cancels and just becomes 2 meters per second, or 2 times 9.81 meters per second, plus 4 meters per second equals VF. So I will plug this in now. The answer is VF equals 23.62 meters per second. Never forget units. 23.62 meters per second. How much slower would the ball be going if it was dropped from rest? So the reason this question has a star around it is because I just wanted you to think about this question intuitively. So no formulas, no nothing. What do you think the answer would be? Because I think you're likely to get it right, but I'm going to go through the reasoning with you. So if you have a ball that is in free fall, then the force, wow, that was a bad line. The force acted on it causes a gravitational acceleration of 9.81 meters per second squared. Then the area under this graph, t, is the velocity after a time t. So it is a times t equals v, which then gives us a graph that looks like this. V versus t, where it is the area under this would give us position, but we are not looking for the area under this. We are just looking at this graph where if you were to start from a velocity of, let's say, 4 meters per second now, the difference at every point in this graph, at every point of time, is still 4 meters per second. So no matter how long ago the ball was dropped, the difference in velocities is still 4 meters per second. That is the answer. See how much easier this star was than this one up here? So, last question. A rock is dropped from rest from a height h. This is just a full variable form question. Write in variable form a solution to the amount of time it takes to get to the ground. So we want g in variable form, or a equals g. We have h equals h, and then we have vi equals 0. That's the only term that's not in terms of itself. 0 meters per second, since it says dropped from rest. So the amount of time it takes to hit the ground, so t equals question mark. We are looking for t in terms of this. So we are going to be using the equation delta x equals VIT plus 1/2 AT squared. So we get the answer is delta x is h equals VI, so 0 meters per second times the time plus 1/2 times g, so I'll just put g up here, times t squared. So we multiply both sides by, so actually let's just rewrite this. We have h equals g over 2t squared. We multiply both sides by 2, and then divide by g, and we get 2h over g equals t squared. Then we take the square root and get t equals, let's name this t naught for the next problem. T naught equals radical 2h over g. So this is our answer. T naught equals radical 2h over g. Now, give the quantity above a value t naught, which we just did. Now, assume you drop the rock from a height of 2h. How long does it take to hit the ground in terms of t naught? So, for this problem, you now plug in, you now have just two solutions. So you have the first equation, which gives us this value, which is, oh, that's not what I went through, that was yesterday's video, which is T0 equals radical 2g, radical 2h over g. I'll just erase that and make it neat because this is important. Radical 2h over g. Now we're going to form a new value, which I will call capital T, which equals to the same thing, the same guidelines that were set up here, except now h equals 2h, 2 mini h. So we have VIT, which is 0 meters per second, plus 1 over 2 g t, oh wait, no, this is supposed to be 2h equals plus 2t squared. And then we get 2h equals 1/2 gt squared. Then we multiply both sides by 2 to get rid of the 1/2. Then we get 4h equals gt squared divided by g. 4h over g equals t squared. Square root, let's make this capital T again, square root. And we get t equals radical 2 times, well, I'm just taking a 4, or 2 out of this 4, times 2h over g. And then we can take this 2 out of here by taking the square root of it, so it's equal to radical 2 times radical 2h over g. And then we know that radical 2h over g is also our value for t naught. So we have t equals radical 2 times t naught. And that is what our answer is looking for. We have big T in terms of t naught. If you have any questions, let me know in the comments. This is a really fun unit, in my opinion, one of the best that there is. And yeah, it only gets better from here. Let me know if you want me to cover more 1D kinematics or if I should move on to 2-dimensional kinematics. I can make a lot more problems, practice, all that. I will probably do 2 more videos on 1D kinematics or just 1 more, and then I'll move on to 2D, which is where it really gets fun. Thank you for watching and have a great rest of the day. Like and subscribe. Thank you.